In this video, we're going to go over epoxides. Now, epoxides are just a special type of ether. They are cyclic three-membered rings. So they're an ether because you have an oxygen that's attached to two carbons, except in this case, all three of these atoms, the oxygen and two carbons, are in a three-membered ring. Now, we learned previously that three-membered rings have lots of ring strain. For a couple of reasons. First, all of the atoms in these rings are sp3 hybridized. Now that means ideally they want to have 109-degree bond angles. When they're stuck in a three-membered ring, however, the bond angle is about 60 degrees. So since that 60 degrees is far from the ideal 109.5, it causes a lot of angle strain. Second, there's a lot of torsional strain because any sort of groups that are attached to the carbon, such as this and these, are going to clash with one another in space, and it's going to end up with a lot of torsional strain. So we have a lot of ring strain associated with epoxides. Now, because they have a lot of ring strain, they're very reactive. And specifically, epoxides are susceptible to nucleophilic attack. Epoxides are synthesized from alkenes using peroxy acids. And the peroxy acid can be written in two different ways. You can either draw it as RCO3H or MCPBA. Now, when this peroxy acid is treated with the alkene, we're adding an oxygen across the double bond, and the oxygen and the ring will always form on the same side of the double bond to give a syn addition of the oxygen. So we can either draw it as, or show it as the oxygen as both wedges forming this three-membered ring, or as both dashes. But we're just illustrating that this ring is forming on the same side. Now, epoxide formation is stereospecific. That means if you have groups attached to the double bond in either the cis or trans stereochemistry, we're going to maintain that stereochemistry with the formation of the epoxide. So for example, we're starting with a cis alkene here, and we're treating it with MCPBA. Now, we know that this is going to form an epoxide, and we know the epoxide will be in a syn addition form. But now we want to illustrate the stereochemistry of the two methyl groups that are attached to the double bond. Since they started out as cis, they're going to end up as cis, and we can show that as either drawing them as both wedges or as both dashes. So either way, both of these are drawn in the cis conformation. It's also the same for a trans alkene. Now with a trans alkene, the way that we draw it, so here we have two methyl groups that are trans to one another. Now it's going to look very strange if we draw this epoxide like this, okay? So we never really see this type of angle with bond line structures. So this is not an appropriate way to draw an epoxide with a trans alkene. Instead, what we're going to do is we're going to draw our epoxide, our three-membered ring, and then we're going to illustrate the stereochemistry of the two methyl groups by drawing one as a wedge and one as a dash. It doesn't matter which one you do as long as you have one as a wedge and one as a dash. Now this is a chiral molecule, so you would also form its enantiomer. Okay, so we want to maintain our stereochemistry when we're dealing with stereospecific alkenes. I said before that epoxides are susceptible to nucleophilic attack. When they undergo nucleophilic attack, it leads to ring opening. Okay, and this is driven by the fact that we have a lot of ring strain associated with our three-membered ring. So in our first set of conditions, we have acid-catalyzed epoxide ring opening. Now this is always going to involve a little bit of acid as well as a weak nucleophile. So here we have an epoxide. We have our acid catalyst, and we can either have water or methanol or some sort of alcohol. Now these structures here are going to act as our nucleophiles. And we know that water and methanol are weak nucleophiles. So in this mechanism, the oxygen of the ether is going to go and grab the acidic proton. What we're doing here is creating an epoxide intermediate that is even more reactive than just a regular epoxide. The purpose of this is to encourage the nucleophilic attack by these weak nucleophiles. Now at this point, and we will go ahead and use methanol as our nucleophile. At this point, the methanol is going to come in and it's going to attack one of the two carbons of our epoxide. Now we need to decide which carbon it's going to attack. So we have a positive charge here. And what that means is the carbons adjacent to the positively charged oxygen can donate a little bit of their electron density and share some of that positive charge amongst them. Now here we have a tertiary carbon versus a primary carbon. This one is tertiary because it's attached to 1, 2, 3 other carbons. This one is primary because it's attached to one other carbon. Now in the case of our primary versus our tertiary carbon, we want to think about which one is more likely to hold a partial positive charge. And we learned with carbocation stability that tertiary carbocations are the most stable. So our tertiary carbon is more likely to donate its electron density. That's going to give it a slightly positive charge. Okay, so it's donating, I'll just show a little bit of its electrons towards that oxygen. So now our methanol is going to be attracted to that tertiary carbon. It's going to come in, attack the carbon, and that will cause the electrons between the carbon and the oxygen to break, and they'll go up and give the electrons to the oxygen atom. Now the oxygen of the methanol is now going to be left with a positive charge, and we'll get rid of that by having something come in and remove the extra H, and another methanol can do that. Actually, let me change the color. It'll take the H, give the electrons back, and we've now created a molecule that has an ether functional group and an alcohol functional group. Now let's take a look at the same acid-catalyzed ring opening when we're dealing with an epoxide that contains a primary versus a secondary carbon. So in this example here, we have a carbon attached to one other carbon, so that's going to make it primary. Then we have a carbon attached to 2 other carbons, so that'll make it secondary. Okay, so with this reaction, it's the same thing. We have the oxygen go and take the acidic hydrogen. This time we'll go ahead and use water as our nucleophile. But now water has a choice. It can either attack at this carbon or this carbon. Now in the case of a primary versus a secondary carbon, we know that tertiary carbocations are the most stable. Secondary is less stable, and primary is really not stable at all. Now in the case of donating electron density and forming that partial positive charge, the difference between a primary and secondary carbon is not very great. So the secondary carbon doesn't really form that much more of a stable partial positive charge than the primary carbon does. So in the case of a primary versus a secondary carbon, we're going to choose our carbons based on sterics. Now it's a lot easier for our nucleophile to attack the primary carbon because it is less hindered. So that's what we're going to see in these particular cases. our water will attack the primary carbon and give the electrons to oxygen. Again, we have the positive charge on the water that just did the nucleophilic attack. And so our last step is going to be another water molecule coming in and taking that extra H and giving the electrons to oxygen. And this allows us to create a diol. So to summarize, with this type of ring opening, if our epoxide is unsymmetrical and we're dealing with a primary versus a secondary carbon within the epoxide, the nucleophile is going to choose the primary carbon, and that has to do with sterics. Now, if we're dealing with primary versus tertiary, because the tertiary carbon forms such a strong or a stable partial positive charge, it's going to choose the tertiary carbon. And if we're dealing with secondary versus tertiary, we're also going to choose the tertiary carbon. Okay, this has to do with what's known as the electronic effect. Okay, and those tertiary carbons have such a stable partial positive charge, it makes them a stronger electrophile. Now we can also break open epoxides using strong nucleophiles. And in these reaction conditions, the nucleophiles will always attack at the least substituted or least hindered carbon. Okay, so we don't have to worry about the steric or electronic effect when we're dealing with strong nucleophiles. So for example, we have this epoxide here. We are treating it with sodium ethoxide. Now the actual molecule acting as the nucleophile is the ethoxide. And again, the sodium is just there to stabilize the negative charge. Now these are two-step reactions. I'll show you the purpose of the water in the second step in just a second. Okay, so now for our nucleophilic attack with the strong nucleophile, we're going to go and the ethoxide is going to attack the least substituted carbon, which is going to be the one right here. Now it really helps in these cases to number your carbons, just so you can keep track of where everything's going after you break open the ring. Okay, so I'll just number the 4. We also have a methyl group here that I can number as number 5. So our ethoxide is going to come in and it's going to attack carbon number 3. That's going to cause the bond between carbon 3 and the oxygen to break, and the electrons are going to go up onto the oxygen. Now there's no acid in this solution, so the oxygen is neutral and will ultimately get a negative charge. Okay, so we have 1, 2, 3, 4, 5. Then we have our ethoxide here. We still have an oxygen on carbon number 2, and because that oxygen just got another set of electrons, it now has a negative charge. So the purpose of the water is to protonate the oxygen to get rid of that negative charge and to turn it back into a neutral molecule. And so we get the result of this particular nucleophilic attack. So examples of strong nucleophiles are mainly going to be things that have negative charges, such as ethoxide, methoxide. So we've got the oxygen with the negative charge. Hydroxide can also act as a strong nucleophile. We have the cyanide ion, which allows carbon to act as a nucleophile. Anything with sulfur. So sulfur acts very similarly to oxygen. So sulfur with a negative charge is a strong nuke. Lithium aluminum hydride, which we saw in the alcohols chapter, this allows hydrogen to act as a strong nucleophile, so we can actually add hydrogen to the molecule. And lastly, Grignard reagents. Grignard reagents allow us to add R groups to an epoxide. This is very useful as a carbon-carbon bond forming reaction. Now let's take a look at how epoxides would react with Grignard reagents. So we'll go ahead and use this epoxide and treat it with a Grignard that has a methyl group. Now if you recall from the alcohols chapter, Grignard reagents are very strong nucleophiles, and the electrons between the carbon group, the methyl group, and the magnesium are the electrons that are going to act as our nucleophile. So we will show our electrons going and attacking one of the carbons. Now the carbons are equally substituted, so it doesn't matter which one you choose. I'll go ahead and show it attaching to carbon number 3. So it'll attack carbon 3, it'll kick the electrons up onto the oxygen atom. Now at this point, we have a bond between carbon 3 and the methyl group. So we've just formed a carbon-carbon bond and added a carbon to the molecule. We also have the oxygen on carbon number 2 that now has the negative charge. This is going to be temporarily stabilized by the magnesium bromide until the addition of water. And water will serve as the proton source to protonate this oxygen and turn it into an alcohol. Okay, so in previous chapters, we saw that Grignards plus carbonyl-containing compounds form alcohols. And they add carbons. And so we're seeing in this chapter that a Grignard plus epoxides act exactly the same. They'll form an alcohol and add extra carbons. So this will be useful when you're doing your synthesis problems. Now when it comes to the stereochemistry of ring opening, the nucleophile will always attack from the side of the molecule opposite from the epoxide. So for example, we have an alkene in a ring here. Now when we treat it with peroxy acid, we know that we're going to form syn addition epoxide. We've illustrated that here. Now, when hydroxide, our strong nucleophile, comes in to do a nucleophilic attack, and since this is a strong nucleophile, it's going to attack to the least hindered carbon. It'll come in and it's going to attack from the opposite side of the epoxide. Now, currently our epoxide has formed above the plane of the ring. So that means the nucleophile is going to attack from below the plane of the ring. Now it'll attack our least hindered carbon and give the electrons to the oxygen atom. So now our hydroxide that we've just attacked is going to be a dash. The oxygen from the original epoxide will remain as a wedge. So what we get is inversion of configuration at the site of the nucleophilic attack. Then, when we go ahead and treat this molecule with a proton source such as water, we'll take the H, give the electrons, and this is an example of how we would form an anti-diol, which we have seen in previous chapters. To summarize the site of the nucleophilic attack when we're dealing with the unsymmetrical epoxides, when we have acid-catalyzed conditions with a weak nucleophile, remember that weak nucleophiles are fairly slow. When we have a primary versus secondary carbon, the nucleophile is going to choose the primary carbon, and that has to do with sterics. The electronics of a primary versus a secondary carbon are not that different, so the nucleophile is going to go to the carbon that's most easily accessible. However, when we're dealing with secondary or primary versus tertiary carbons, the nucleophile will always go to the tertiary carbon. That has to do with the electronic effect. And that's because a tertiary carbon provides a much more stable partial positive charge, which makes it a stronger electrophile. Now, when we're dealing with a strong nucleophile only wants to perform a nucleophilic attack, and it wants to do it quickly. So it's going to choose the carbon that's most easily accessible. So whenever a strong nucleophile is involved, it's always going to choose the carbon that is the least sterically hindered. Okay, so in all of these cases, primary versus secondary, it'll choose the primary carbon. Secondary versus tertiary, it'll choose secondary. And primary versus tertiary, it'll choose primary.